Hello again. I've got problem number 13 from the end of the chapter on momentum. That would be page 287 up on the board right now. I just did this one. It's a conservation of momentum problem. And it's pretty low level, but it involves graphing. I'd like you to be able to understand graphing and how it relates here. So I went ahead and redrew the graphs up on the board here. This is problem 13. So this graph represents, by the way, it's a ball hitting a wall, okay? So that's what the problem is about. And what you've got graphed here is the velocity of the ball as it comes to the wall, and then its velocity changes, and then it leaves the wall. So it comes into the wall with a certain velocity, negative 10 meters per second. It interacts with the wall hits it, it hits the wall, and its speed changes and it bounces back in the opposing direction, in the positive direction. So it comes in like this, bounces off the wall, then goes out like this. We don't know what the speed is that it leaves the wall. It doesn't leave at positive 10, so it's lost some of its kinetic energy due to interaction with the wall. And what we want to do is find that velocity. So the major goal here is to find v0, the final speed of the ball after it's impacted the wall. They tell us that the mass of the ball is 250 grams. They also show us a graph of the force exerted on the ball by the wall. Okay, so the ball comes in traveling in the negative direction, hits the wall, and then bounces back. So while the ball is in contact with the wall, that's during this 8-second interval, the wall has a force acting on it of 500 newtons. Okay, so that's the information you're given. These two graphs and the mass of the ball, and you're asked for the final speed of the ball as it bounces off the wall. So to do this problem, you use the definition of impulse. So capital J represents impulse is equal to the force applied to an object times the time that force is applied. We have all that information in this bottom graph. So let's multiply that, and remember the area underneath a force versus time graph is impulse. So doing the calculation, we get 4 Newton seconds, and since it's a positive value, that means it's the impulse is applied to the ball in the positive x direction. That's why I've got this over here. Okay, it is a vector quantity, and you don't really need to use I hat and j hat when you're just talking about a one-dimensional problem. Positive direction means it's in the positive x, negative direction means negative x. Here, excuse me. So, the impulse momentum theorem tells you that impulse is also equal to the change in the momentum of the object. That's also the change in momentum of the ball. It's 4 Newton seconds. But we can express that change in momentum as the final minus the initial momentum. So that's going to be the mass of the ball times its final velocity minus the mass of the ball times its initial velocity. We know everything there except for the final velocity, so we're down to the point where we can plug in numbers now. And okay, so J is equal to 4 Newton seconds. We just determined that. That's got to be equal to the mass. Here I'm factoring M out. So here's the mass of the ball, 1/4 kilogram. And then all of that is multiplied by the final velocity minus the initial velocity being negative 10 meters per second that you can get off the top graph there of velocity versus time. If you multiply both sides by 4 to get rid of this 1/4 over here, and then divide by kilograms, this side becomes 16 meters per second. We've gotten rid of the mass term or factor over on the right hand side of the equation. That leaves us v0 plus 10 meters per second, so easy enough. v0 is 6 meters per second. So the ball rebounds at only 6 meters per second while it was coming in at 10 meters per second. So it lost some of its momentum, transferring it to the wall, and the wall's firmly attached to the earth, so basically the ball has imparted momentum to the earth, so actually changed its speed. Okay, that's it. And that problem was a direct use of the impulse momentum theorem. which says that the impulse, which is the force times the time the force is applied, is equal to the change in momentum of an object. That's it.